thank organizers for giving me a chance to give a talk in the conference. Here I give a talk about my recent publication, Model-Independent Constraints on Type 1a Supernova, Lycov Hyperparameters, and Reconstructions of the Expansion History of the Universe. My name is Hanwool, and I'm a PhD student of Arman Shapielu in Korea Astronomy and Space Science Institute. He's also professor in University of Space Science and Technology in Republic of Korea. This research have two co-authors, Ryan Keeley and Benjamin Luilier. For more detail, please see the link to the publication on the slide. First, I'll give a brief introduction about the study. Type 1a supernova, in short SN1A, are used as standardizable candles for distance measurement and have become one of the important portion of modern cosmology. The standardization is purely empirical and requires SN1A Likert fitting model with a number of parameters and hyperparameters. The Likert hyperparameters are usually constrained based on assumption of cosmological model. And the main purpose of this study is to relax assumption of cosmological model when we constrain the Likert hyperparameters. To do so, we use the joint Likert analysis compilation, in short JLA compilation, which have Likert parameters information based on sawtooth filter. The JLA compilation is introduced by Betole et al. In 2014, and sawtooth filter is introduced by Guy et al. In 2007, and also described in Mosher et al. In 2014. The JLA compilation provides observed B-band peak magnitude, stretching of the light curve, and supernovae color at maximum brightness. The provided Likert parameters are based on the formula introduced by Tripp in 1998. You can see that the equation, the formula includes all of three parameters that I already mentioned in the previous slide. And they are all included in the JLA compilation. Also, there are the Likert hyperparameters, also called nuisance parameters in the formula. Alpha and beta indicates proportional factors of x1 and c, while MB1 and delta M describes MB, which indicates absolute B-band peak magnitude. It depends on the value of stellar mass of host galaxy. If stellar mass of host galaxy is lower than 10 to 10 solar mass, MB becomes MB1. Otherwise, MB equals to MB1 plus delta M. And these four Likert hyperparameters need to be constrained in model-independent way. To constrain the hyperparameters in model-independent way, we will apply the nonparametric method to reconstruct the distance modulus and expansion history of the universe. This method is introduced by Shapielu et al. In 2006 and Shapielu 2007, and improved by Shapielu and Clarkson in 2010, and Shapielu et al. In 2018. This method starts from initial guess of distance modulus, but generates model-independent reconstruction of distance modulus with lower chi-square value after numerous iterations. You can see the iterative formula to do the iteration on the slide, where C2 minus 1 indicates inverse of covariance metrics from JLA. W is the weight. Delta is the smoothing width determined by the previous studies about the smoothing method, and delta mu n is a residual of distance modulus. We can also calculate chi-square value from delta mu n and C2 minus 1. Next, we chose three different cosmological models to compare the hyperparameter constraints with those from the reconstructed distance moduli. One is ΛCDM, lambda cold dark matter model, which is concordance model in the present time. Another is CPL, Chevallier-Polarski-Linder parameterization, which parameterize the equation of state parameter of dark energy. The other is PEDE, Phenomenologically Emergent Dark Energy model, which claims no effect presence of dark energy in the past, then emerging at later times. You can see that each of three models have different descriptions of the equation of state parameter of dark energy, denoted as WC. And this corner plot shows constraints from the reconstructions and the three different models. The red color indicates contours from reconstructed distance moduli, while blue, green, cyan color indicates contours from ΛCDM, CPL, and PEDE, respectively. You can see that the contours are consistent with each other, except the uniform distribution of MB1 from reconstructions. MB1 from reconstructions shows uniform distribution, since SN1A alone cannot constrain an absolute distance scale. Next, this corner plot concentrates on constraints from the reconstructions by dividing them into two redshift bins. One is 0 to 0.65, colored in maroon, and another is 0.65 to 1.3, colored in magenta. We can see that the statistical deviation between the contours from the two redshift bins are not large enough, and the relative size of the contours are different. The first corner plot shows that constraints from reconstruction and predictions of three different models are consistent with each other. It also shows that distance moduli constructed from the JLA data are mostly independent of cosmological model. Lastly, the second corner plot indicates the Likert hyperparameters are constrained mainly by the data, including the low redshift bin. This time, we explore possibilities of the expansion history of the universe with higher likelihood than that of ΛCDM. To do this, we have reconstructed the expansion history of the universe on parametric space of Likert hyperparameters explored by Markov Chain Monte Carlo analysis. Also, we reconstructed the parameters which describe the dark energy properties and compare them with predictions of the ΛCDM, CPL, and PEDE model. So this figure shows the distribution of chi-square from reconstructions and three different models. We have selected only 100 set of values of Likert hyperparameters from the MCMC samples randomly. And this figure shows only reconstructions with 1,000 iterations, but we also consider reconstructions with iterations lower than 1,000. And lastly, we choose only reconstructions with chi-square value lower than chi-square value, which corresponds to ΛCDM best fit. So based on the equation on the slide, we have derived the expansion history of the universe and the two parameters which describes the dark energy properties from the reconstructed distance moduli we chose in the previous slide. Among these among three new parameters shown on the current slide, we adopt the own parameter introduced by Sani, Shafilu, and Starobinsky in 2008, since it is equal to the matter density at present time when the background model is the ΛCDM model. In other words, this parameter can be useful to test the ΛCDM model. And these figures shows the reconstructions and the ΛCDM best fit so that we can compare between them. Top left panel shows relative deviation of 8,000 reconstructed distance moduli from the best fit ΛCDM model with a constant shift, while others show reconstructions of the other parameters derived from them. we have produced 20 reconstructions from each of the 4 different initial guesses and each of 100 random light curve hyperparameter values. In these figures, we can see that reconstructed expansion history of the universe and parameters which describe properties of dark energy are in good agreement with prediction of the ΛCDM model. Also, reconstructions of expansion history of the universe and the other parameters show considerable flexibility. Now, I'll briefly summarize the talk before finishing it. Our research using the JLA compilation shows that constraints from model-independent reconstructions are in good agreement with predictions of 3 different models. Also, it shows that distance moduli constructed from the JLA data are mostly independent of cosmological model. Lastly, reconstructed expansion history of the universe are consistent with prediction of the standard ΛCDM model with considerable flexibility. Thank you for your listening, and please feel free to ask questions or give comments.